I'm going to draw a picture of two cars here. Probably not a very good picture of two cars because that would require me to be a good artist, but you'll recognize them here. Here's the first car. We'll call it our blue car. And the second car we'll call our red car. So blue car, red car. They're going to collide with each other. They're going to hit each other, and they're going to apply forces on each other. I want to know how the forces compare. You ever heard of Newton's third law? For every, you have heard this, I know you have. For every, say it? Yes, for every action, there's an equal and opposite reaction. I don't like actually stating it that way, personally, even though that's the way it's usually stated, because I think that can lead to a bit of a misconception. But we'll state it that way for now, and then I'll modify it in a few minutes once I explain where that misconception comes from. For every action, there's an equal and opposite reaction. Let's draw a free body diagram of the blue car. When that blue car collides with the red car, there is a force acting on the blue car to the left. We'll call that F1. Let's say its value is 5,000 newtons. If Newton's third law holds, for every action there's an equal and opposite reaction, there should also be a second force, we'll call it F2, of 5,000 newtons. Is that correct? What do we know about that force of 5,000 newtons? Besides the fact that it's equal in magnitude, 5,000 newtons, it's for every action there's an equal and opposite reaction. So that force that we're calling F2 of 5,000 newtons should be to the right. Is that correct? That's the misconception that the way we just stated Newton's third law often leads to. This is wrong. If we draw it like this, that would tell us the net force acting on the object is zero. These forces balance, right? If Newton's third law, if we've interpreted Newton's third law correctly, and Newton's third law always holds, the net force acting on an object would always be zero. And an object at rest would always remain at rest because you can never unbalance that force because it would always be an equal and opposite reaction. An object in motion would continue in motion in a straight line always because you could never have an unbalanced force. So something's wrong here, either with our understanding or interpretation of Newton's third law or the fact that Newton's third law only holds sometimes. Well, let me tell you what it is. Newton's third law always holds. Always. We just went through this in Physics 30 with an electric force problem. The forces were always equal and opposite. So it's not a matter of the law not holding sometimes, it's a matter of our interpretation of the law. Does anybody see where our interpretation is wrong? Does anybody see what we've done wrong with our diagram up on the board? Let me rephrase Newton's third law. Here's the way that I like to state it, because I think this leads to a better understanding of what's really happening. Instead of saying for every action there's an equal and opposite reaction, which is absolutely correct. Your grade 6 teacher or whoever taught it to you that way was absolutely correct when he or she taught it that way. They weren't lying. They may not have completely understood it. They may or may not have completely understood. It's actually kind of a hard one to understand. Sounds like the easiest one. I think it's actually the hardest one. But they taught it to you correctly. The way that I like to state it, though, that leads to a better understanding, I think, is this. If object A applies a force on object B, then object B will always apply an equal and opposite force on object A. Does that make sense what I just said? If object A applies a force on object B applies an equal and opposite force on object A. Why do I like to state it that way rather than the first way? Let's call this object A and let's call this object B. Let's get rid of that second force for a second, okay? Object B applied a force of 5,000 newtons on the blue car here, right? If object A applies a force on object B applies an equal and opposite force on object A. Where's the other force? Where's the reaction force of 5,000 newtons? Not where I drew it the first place. It's right here. We'll call this one F2 of 5,000 newtons. If object A applies a force on object B, that's this force. Object B applies a force on object A, that's this force. We're talking about equal and opposite forces, but equal and opposite forces that act on two different objects. Does that make sense? Now we have a net force acting on both of them, right? Now both of them will accelerate. This guy accelerates backwards, this guy accelerates forwards. If I just say for every action there's an equal and opposite reaction, it often leads to that first problem that we had, there is no net force. But we forgot, when we stated it that way, that we're acting on two different objects. Therefore, there is a net force on both of the objects, and they'll both accelerate. So we're going to state it this way. If object A applies a force on object B will apply an equal and opposite force on object A. Let's take a look at some action-reaction forces here. If my hand pushes on the wall, like look, right now, I'm leaning on the wall right now. My hand is pushing on the wall, right? What's the action force? What's the action force when my hand pushes on the wall? Easy. It's my hand on the wall. What is the equal and opposite reaction force? Look, I'm leaning on this wall. If this wall isn't here, what would happen to me? I would fall over, right? If I'm not falling over, then something must be pushing on me to keep me from falling over. What's pushing on me, Scott, to keep me from falling over? The wall. The wall pushes on me with the same force as I push on the wall. So the action force there would be my hand on the wall. The reaction force would be the wall on my hand. Two separate objects. Either one of them or both of them could accelerate. We're not talking about a net force of zero, because although these forces are equal and opposite, they're acting on two separate objects. One of them is acting on my hand, one of them is acting on the wall. My foot kicks a soccer ball. What's the action force? How many people are soccer players here? When your foot kicks a soccer ball, what's the action force? Your foot on the ball. If your foot does not apply a force on the ball, then what's going to happen to the ball? Yeah, nothing's going to happen to it, right? If it's at rest, it's going to stay at rest. If it's moving, it's going to stay moving at a constant speed. Your foot must apply a force on the ball. What's the reaction force? The ball on your foot. The ball applies a force on your foot. You ever get up in the middle of the night to go to the bathroom, or you hear this sound, or maybe you got to go close a window or something like that? Get up in the middle of the night from time to time, right? Occasionally. It's dark. You walk past the end of your bed end. You kick the end of your bed with your bare foot. You stub your toe. Why does your toe hurt? Why does your toe hurt? Not because you kicked the bed. Because the bed kicked you back. That's why. Your toe applied a force on the bed applied a force on your toe. It doesn't hurt you to apply a force on the bed. It hurts the bed. It hurts you for something to apply a force on your foot or on your toe. It's the bed applying an equal and opposite force on your toe. Does that make sense? My hand throws a ball. I throw a baseball, or I throw a volleyball or something, football, whatever. My hand throws a ball. The action force is the force of my hand on the ball. If the ball is forward, right? It's because my hand is pushing on the ball. But there's also an equal and opposite force of the ball on my hand, right?